Section 21.2. Okay, this is the beginning of chapter 21, carboxylic acids and their derivatives. We're going to start here with the general introduction to these. The formula we're going to take here is with the Y, so the acyl group with a Y. Y here to distinguish those that we're going to be talking about, carboxylic acids, the amides, esters, thioesters, anhydrides, and chlorides. You can make bromides too, but they're not as prevalent. Mostly we deal with chlorides. Now, that's distinct from, and these mechanisms are not when Y equals H or R. That makes us to do with the aldehydes or the ketones. They do not undergo this kind of reactivity because basically Y here can be looked at as a leaving group. And so the reactivity patterns for the carboxylic acid derivatives are all unique because of that. So what happens here is we get a nucleophile to attack. Now we know that the carbonyl carbons are electrophilic. The nucleophile attacks. Of course, the carbon's got to have 2 electrons swing up. This produces an intermediate. That intermediate has a name, and I want you to learn that name, know it, recognize it. You're going to see it a lot. The tetrahedral intermediate. Now, what does that come from? Well, we had an sp2 hybridized carbon. What's its geometry? It's trigonal, right? Here we have 4 different things attached. It's an sp3 carbon, so it has a tetrahedral geometry, hence the term the tetrahedral intermediate. And we're going to see this intermediate over and over and over again. And if you understand it, recognize it, and can apply it, then you'll be able to solve almost all the reactivity and the mechanism of these kinds of compounds. Now, the lone pair on the oxygen is going to come back down, okay? If the nucleophile gets kicked out, we go back. So most of the time these are reversible reactions, and we're going to look at that when we look at the mechanisms. But to move forward, we need to kick out the leaving group, the Y group, and if we do that, you see, we then have this nucleophile. So we have all of these derivatives. We're going to see this common reaction pattern for them. Understand the general, then be able to apply it to each one specifically. Now, let's talk for a minute about their stabilities, because the stabilities are going to be the reverse of the reactivities. And so if we start with the amide, it's more stable than an ester. And that is more stable than a thioester, which is more stable than an anhydride. Now that may be a new functional group for you. The anhydride is like an acid reacting with an acid. And you put two of them together, you lose water, hence the term anhydride without water. Okay. Not quite hydro, but you get the picture. And then this is more stable. So this is relative stability. Okay. And that's more stable than the acid chloride. Now, if that's the order of stability, it's the reverse of the relative order of reactivity. So the acid chloride will be the most reactive of these species. So that means that we can readily convert an acid chloride to an anhydride, to a thioester, to a carboxylic acid ester, or to an amide. That's very straightforward and easily done. Likewise, we can convert an anhydride to a thioester, to an ester, and to an amide in a very easily done and straightforward manner. And then we can continue that pattern. The thioester can be converted to the ester, and the thioester can be converted to the amide, and we can even convert an ester into an amide with the right conditions. So now let's take a look at how we would do this in a general sense. Acid chlorides are highly useful because if we put them at the center of a wheel, we'll see that we could react this with water, and what would it do? It would hydrolyze to the acid. We can react it with a carboxylate, and we want to typically do these symmetrically. There are occasional uses for unsymmetrical anhydrides, but not so many. Again, that's the anhydride. So we had the carboxylic acid, the anhydride. You should be able to look at these formulas and know the name, and from the name, think of a molecular structure. We can add a thiol and produce a thioester. If we add an amine, and we have to have two equivalents of an amine, we need at least one hydrogen on the amine. We can make an amide, and if we react this with an alcohol, we can make the ester. So 1, 2, 3, 4, and hydrolysis. So then what you should do is make for yourself a little chart of each one of these. Put the anhydride at the center. Well, the anhydride would not be converted into the acid chloride very easily because it's more stable than the acid chloride, but you would be able to make each of the other inner conversions in a straightforward manner. The thioester would have one less reactivity. The ester, we basically can only convert to the amide unless we have some very special conditions. and those are really beyond the undergraduate level course. Okay, so that's the general introduction to carboxylic acid chemistry, and that's it, we're done. The rest is just specifics, but that's a lot to cover. So get ready, we're going to look at some details now.